evangelist with AWS, focusing on AI and machine learning, and I've been with AWS for almost 3 years now. My topic today is, as you can see, deep learning for developers. And I wanted to call it deep learning for humans, because it's really deep learning for normal people, not people who have 5 PhDs and a 200 IQ, which I have neither. So it's really, my point today is really to show you that if you can read and write 50 lines of Python, you can do deep learning, okay? And I really want to show you how easy actually it is to understand the basics, the concepts of deep learning, and then to actually write the minimal code and the minimal processes that are needed to use deep learning in your apps. Okay, so we'll start with an introduction to deep learning. This is a little bit theoretical. I tried to make it as easy as possible with as little math as possible. But okay, feel free to yell and throw stuff at me if it makes no sense. But it usually does. Okay, and then we'll go through demos because again I want to run some code and I want to show you that anybody in the room can do it. So we've all heard about neural networks, okay? This is the technology that deep learning relies on. Machine learning in general relies mostly on statistics and math, and we can use a combination of algos. And deep learning, which is a subset of machine learning, uses neural networks and only neural networks. So we need to understand what a neural network is, and we should start by understanding what a neuron is. And what we're trying to do here is we're trying to approximate the biological neuron, the brain neuron. Okay, so brain neurons, what we know of those neurons is that if they're stimulated enough, they fire, right, an electrical current, and if they're not stimulated enough, they don't fire. You could say that even if mine are stimulated enough, they probably don't fire, but that's just because I'm old. But anyway, that's what we're trying to build here. So a neuron is really a collection of inputs, okay, signals. Each input is associated to weight. And the first thing we're going to do is basically take each input, multiply by each weight, and sum everything. And we call this multiplied and accumulate. Okay? And those inputs and those weights, they're just floating point values. Okay? They're just information, data samples that we feed to the neuron. Okay? So that's the multiply and accumulate. And really that's what deep learning is all about, multiplying and adding stuff. So you don't need, again, a math PhD to do this. The problem, of course, is that this function here is a linear function, right? If you change the inputs, the x's, then the result will vary in a linear fashion. And that's not what we want, because remember, we said that the biological neuron fires or not. There's a limit, there's a threshold that says that, okay, below this threshold, nothing happens. After this threshold, something happens. And that's a nonlinear behavior. So we need to add an extra function after the multiply and accumulate operation, and this is called the activation function. And it's a good name actually, because this decides whether the neuron will fire or not. So over time, a number of functions have been used. The popular one these days is called ReLU. Okay, and you can see it's a very simple function. If the input, so if that U value, right, if the input to the activation function is negative, it could be really, really negative, then the output of the activation function is 0. So the neuron doesn't fire. Okay? If the input to the activation function is positive, then we output that value itself. Okay? And it could be very, very large. Okay? So this is pretty much the behavior we want, right? If the neuron is stimulated enough, we get an output, and it could be a really large output if the stimulation is very, very strong. And if the neuron is not stimulated enough, nothing happens. Okay, and this is how we introduce that nonlinear behavior in a neuron. Okay, so at the core of neural networks, this is what really happens. Okay, take inputs, multiply by weights, and we'll talk about those weights again, of course. Add everything, and run that result through the activation function. So a neuron by itself doesn't do much. It's not really interesting. We need to put them together to build networks. So this is probably the simplest neural network you could build. So an input layer where we will push our samples, our data samples, an output layer where we will read some results, and in the middle, at least one layer, which we call the hidden layer. And in this case, we call it a fully connected layer because, as you can see, each neuron is fully connected to all inputs, fully connected to all outputs. Okay, so it's a full mesh. Okay? And in case you wonder why these things are, this thing is called deep learning, is because you tend to have many hidden layers. Okay, so like you stack them up like pancakes, I guess. Except they're horizontal. But, or you could short that out as well if you want. Okay, but in this case, we use just one hidden layer. So how does that work? Well, we need data, right? And yes, I know it's a matrix. Take a deep breath. You'll be fine. You will all survive this. So I need data to train my network on. Okay, so for the sake of this discussion, let's say we're trying to classify images. Okay, so we have a collection of images. And to make things quite simple, we're going to flatten all these images into vectors, right? And so each individual pixel value is a value in this vector. Okay, so x1 is my first image, right? Each of these individual x things is pixel value, right? x2 is the second sample, etc., etc. xn is the last sample. Okay, so let's just keep it simple. Okay, take images, flatten them into vectors, and we use the pixel values as features, okay? And of course, we know what those images are. So let's say, again, we have 10 categories. Okay, we have maybe dogs are category 2, maybe cats are category 0, maybe elephants are category 4, etc., etc. And so, of course, we know what those images are, okay? So we can build labels, okay, in a vector, and for each of the samples here, we're going to provide the corresponding category number. Okay, so that first image here is a dog, and the second is a cat, and the last one is an elephant. Okay, and we know because we know what the data set looks like. Okay, this is called supervised learning. You have data, and you know what that data is. Okay, so classification is an example of supervised learning. You can also do unsupervised learning, and clustering would be an example of that. Okay, taking 1 million samples and trying to group them in 10 groups. Without knowing what those groups are, just letting the algo decide. Okay, clustering, again, is unsupervised learning. So, coming back to this. Actually, this is not really useful, right? If you do machine learning already, you know we don't like categorical values. Okay, and the first thing we do is we use a technical one-hot encoding to transform those categorical values. And again, it's a very complicated word to explain something really simple. Let's say, once again, we have 10 categories. Each of those category numbers becomes a vector of 10 bits, and we flip to 1 the bit that corresponds to the actual category. Okay? So this is category 2, so bit 0, bit 1, bit 2, we flip bit 2 to 1. Okay? This is category 0, we flip bit 0 to 1, etc., etc. This is called one-hot encoding, and this is how you deal with categorical variables when you do machine learning. Many reasons which I don't really have time to explain, but you'll see this technique over and over again. This is actually much more expressive, right? Because we could look at those numbers as probabilities for each of the classes. Okay, so when we look at this here, we'll say we know that this sample has a 100% chance of being category 2. When we look at this one, we know it has a 100% chance of being category 4, and 0% for all the classes. Okay? So this is more expressive because when I look at this, I see the number of possible classes and I see the probability for each of the classes. And again, here we have zeros and ones because we know for sure what's in those pictures. But when we're going to predict, obviously, there is no such thing as zeros and ones, right? We all thought computers were about 0 and 1s, but it's all fake. It's all about probabilities. Okay? So no zeros and no ones, only probabilities. So when we will predict, we will see different probabilities. Hopefully one of them will be really, really close to 1, right, showing the right class. But we'll see about that. So how do we actually do this? So if we have a trained network, we could take the first sample, and this is the actual highlight of my talk, the PowerPoint animation here. You can leave now. we'll take that sample, we'll take each feature, put it in a neuron in the input layer, which obviously means that in the input layer, I need to have as many neurons as I've got features. So if I've got, let's say, 1,000 pixels here, I will need 1,000 neurons here. Okay? Makes sense. And then I will run the multiply and accumulates using the weights in the network. I will run the activation functions. Okay, this is called forward propagation. And God willing, I will get, and deep learning willing, I will get zeros everywhere except in the neuron for the right class, okay? Which again requires that I have as many output neurons as I've got classes. So if I have 10 classes here, I need 10 output neurons, okay? So in a perfect world, this is how things would work, okay? But there are two answers we really haven't answered. How do you train the network, right? How do you find the right weights? And will we really get zeros and ones? Right. So we're going to answer that, of course. And what we care about is the accuracy. Okay. Obviously, the number of correct predictions for the data set divided by the total number of predictions. Okay. So the highest accuracy means we've learned successfully how to predict this data set. Okay. So in a nutshell, this is what we're trying to do. Okay. Trying to push. We're trying to forward propagate samples and read some results on the output layer, and hopefully they're correct. But of course, initially it's not going to work like that, because initially all those weights are pretty much random values. Okay, so you know it's not going to be all zeros and ones; it's just going to be random values. There are many ways to initialize those weights, but again, to keep it simple, let's say these are random floats. Okay. So if I take a sample here and forward propagate, I will get something completely wrong on the output layer. Okay. And I won't even get that. It's not even that I will get a 1 in the wrong position and zeros elsewhere. I will just get a random probabilities. But I guess I'm too lazy to fix this animation, which I'm so proud of. But I should. Holiday project. Okay. So initially, we will get fully random probabilities here. Okay. So if you see this network as a math function, okay. So this is the input, and all the weights are the parameters. So let's call this function f. So when I take a data sample and compute its category with f, I get the wrong result, really. Okay. So I need to measure the difference between the real value and the predicted value. And it's not as easy as subtracting one from the other, because obviously these are vectors, right? So you want to measure the difference between two vectors of probabilities. So you use loss functions to do this, okay? And you don't have to worry too much about them, because they are implemented in all the deep learning libraries that we use. Okay? So the loss function will compute the error, which will be again a floating point value between those two vectors. So we could say, well, once we know the error for a sample, then if in a magical way we could go and tweak the weights and try to reduce the error, and then run another sample and do it again. So most of the time, almost all the time actually, we work with batches of samples, not individual samples. I'll explain why in a minute. So what we're going to do is we're going to take a bunch of samples. It could be 32, 64, 128 samples. We're going to run each of them through the model, and we're going to add up all the individual errors, okay? And that gives me a batch error. And now with that batch error, I can make decisions on updating the weights. Okay? It allows for faster training, and it has all the other nice properties as well. Okay, so it's actually called mini-batch training. That's the exact term. So basically, now we know that the purpose of the training process is to minimize loss, okay, minimize error, minimize the prediction error, gradually, batch by batch, by adjusting the weights. Okay, so forward the batch, adjust the weights. How? We don't know yet. And then hopefully we made the right decision. And then do another batch and adjust the weights again, etc., etc. Okay. And if we take the right decisions all the time on those weight updates, then we actually reduce the error gradually. Okay? So this is what the training process looks like. So we have a data set, a training data set. We slice that data set in batches. And again, usually the libraries will do that for us, so less work. We propagate each sample of that batch, one after the other, add up all the errors. We come up with a batch error, and then here comes the magic algorithm, back propagation, which goes back from the output layer to the front layer, okay, to the input layer, which is why it's called back propagation. And layer by layer, it will adjust the weights, each individual weight, in a direction that we know reduces error. Okay? Remember, weights are floats. So, I don't know about you, but me, there's really two options, right? For a float, I can increase it and I can decrease it. Okay? So for each of those weights, here, let's say, this first layer here, I need to decide whether I should increase it a bit or decrease it a bit to reduce the output error. Okay. So back propagation will do it for this layer, and then it will move back on there and do it again and do it again and do it again, all the way back to the input layer. Okay. And then we do this again with another batch and back propagate again. Okay. And again, if we take the right decisions, if we update the weights correctly, we take error down a little bit. Okay. And if you do this for many batches, right? Step by step, you get to a lower error. And eventually, you get to the end of your training set. And this is called one epoch. Okay, you've probably seen this before. And we're going to train for many epochs. It's typical to train for maybe 100, 100, 200, 300 epochs. Okay, so it's a lot of iterative processing, right? Sending a batch, back propagating, and do it all over again, and until you reach the end of the data set, and then starting all over again and again and again. And so gradually, if you take the right decisions, your weights converge to a set of weights, right, that give you a very low error. Okay? And if you have very low error, you have very high accuracy. Make sense? Now the magic thing, obviously, is how could we possibly know if this weight should be increased or decreased, and what about this one, and what about this one, and what about all the other ones? Right? That's the magic bit, okay? And unfortunately, I have to take you back to high school for a minute, okay? I remember derivatives, and half the people are going, oh my God. Should have gone to that DevOps session. I knew it. I knew he was going to say stuff like that. Lock the door. So derivatives, right, give you the slope. Okay? And of course, when you know the slope, you know which way is up and which way is down. Right? Imagine a simple parabolic function like this, right? And take any point in there and take the slope. And now picture that in your head, so you know if you're on the right hand side of the axis, right? Lots of positive values for x. The slope, so the parabolic curve will be like this, the slope is something like this. So if the slope is positive, so if you increase x, well, the output, right, the y value increases, so you're going up. If you decrease x, your y value goes down, so that's where you want to go. Okay, so it's, again, high school stuff. The difference here is these functions have multiple parameters. Right? So y equal x to the power of 2, that's simple. Here, in this example here, in this layer, the output here depends on 3 parameters. Okay? So the error function here really has 3 parameters, not just 1. Okay? So you need to compute partial derivatives. Okay? So that's what backpropagation is going to do. It's going to compute the partial derivative with respect to each weight, and it's going to decide whether to upgrade, to update, to increase or decrease that parameter. That's how it does it. Okay, nothing less, nothing more. And yeah, it might sound weird or complicated if you didn't take a lot of calculus, but that's all there is to it. Okay, and once again, the deep learning libraries do it automatically for you. So 99.9% of the time, you just don't have to worry about it. It just works. So partial derivatives then, okay? That's what backpropagation is going to do, and once it has the slope, it knows how to update the weights up or down to go to a lower values on the error. So as three things here are important as well. So batch size, obviously, right? If you have very tiny batches, you train pretty slow, right? If you have huge batches, you might train faster, but you don't get so many shots at backpropagation. So it might not converge very well, so you need to find a right a middle value here. The learning rate will influence the size of the steps that you take, right? The size of the updates that you make to those weights. So if you have very tiny learning rate, you make very small updates. So you might be moving in the right direction, but very slowly. If you have large learning rates, then you make very large updates to the weights, and they might actually be too large, as we'll see them in. And the number of epochs is actually how many times you will go through the full data set. These are called hyperparameters, and they're critical in getting good results. So the actual optimizer, the actual algo that updates the weights, okay, backpropagation is the overall process. Now, the actual way you update the weights is called optimization, okay? And the granddaddy of optimizers is SGD, was invented in 1951, if you can read that, even before AI and machine learning were even invented. And the way to see it is imagine the error function as just two parameters, right? X and Y, and Z is the error. Okay, so if you plot that thing, let's say it looks like this. So initially, X and Y have random values, like I said. So you start anywhere on that surface, okay? And you compute partial derivatives for X and Y to get the slope with respect to X, the slope with respect to Y, to know literally which way is down. And then you make a tiny update to X and a tiny update to Y, and so you go down a bit, okay? And you know you're in the right direction because again, the derivative told you where to go. And you do it again, and again, and again, and again, and again, and again, okay? And again, by just walking down the mountain, step by step, you will get to very low, maybe not the absolute lowest, but a very low error value, right? And this is what SGD does. Okay. But you see, this is iterative, again. Okay, so we need to do this many times because we tend to take small steps down the mountain. So we need to train long enough to actually get to a low point. Okay. And the step size is really the learning rate. So if you have a very tiny step size, you can understand it will take forever to get here. If you have a large learning rate, you might actually bounce, right? You might take giant steps, and you're unable to go down. So maybe you'll jump from here to here, and then from here to here, and you're taking steps that are way too large to actually get to the low point. So you have to pay attention to that. So SGD is just one way of doing it. And there are other optimizers that you can see here, specifically the ADA family of algorithms, adaptative. And as you can see here, these have a lot of nice properties. They avoid staying stuck. This point here is called a saddle point. You can actually defeat SGD because in this direction, yes, okay, this is a minimum, but in this direction, it's a maximum. Okay, so if you remember from high school, the derivative will be 0 for minimum and maximum. Okay, so if you end up exactly here, then the derivative is 0 in all directions and you stay stuck. Right? So that's not good because you want to go down. So anyway, these optimizer can break, the more modern one, they can break out of those conditions, but more importantly, they can actually detect the slope. They can understand not only where down is, but how steep the slope is, and they can speed up. Okay, so you actually get faster to that minimum point. Okay, so we'll see some of them, ADA, delta, and people come up with more all the time. But of course, life is never easy. And what if the error function looks like this, right? Imagine we start here on the red mountain, and we walk down, and we end up here. Okay, and everywhere we look is up. Okay, Okay, so we get stuck in that local minimum with an error value here that is quite bigger than the one here. So intuitively, it would be more desirable to be here, right? But we just got stuck. Okay. So there's a big debate in the deep learning community on, do these things really exist? And if they do, are they hurting the training process? And how do we break out of those points, etc., etc. Right? So to make a very long story very short, if you're curious about this, I would refer you to this research article by Ian Goodfellow, who's one of the top AI researchers. And he actually figured out that, yes, we can actually see things like this in loss functions for neural networks. But as it turns out, we avoid them. Right? The training process avoids them. And we're not getting stuck in very shallow local minimum. Okay. If you can't sleep, I really, really recommend it. And then you can go and read all the articles that he references, and then you will never sleep again, I can guarantee that. It's fascinating. So, the training process should work, right? And of course we need to measure how well it does. So we keep part of the data, we call that the validation data set. And at the end of each epoch, we're going to predict those samples that the network has not seen yet, okay? And we're going to measure accuracy. And this will give us a sense of how well that trained model, or that model in training, I should say, generalizes to sample it hasn't seen before. Okay? So that's a really important thing, as we'll see. And then once we're done training, we're going to use another data set called the test data set. And this one will just give us, at the end of experimentation, once we're completely done, it will just give us a benchmark, a reference accuracy for this data set. Okay. So training set to train, validation set to check accuracy after each epoch. And once you're completely done, tweaking the model, running the test set to get a benchmark in that model. Okay. And so if you plot everything, it's going to look like this. Okay. The training accuracy will go up very quickly, and then it will plateau. And if you train long enough, it will get to 100%. Okay, guaranteed. Right. Guaranteed. If the network is deep enough, if you have enough data, if you train long enough, you will get 100%. If you look at the loss function, well, no surprise, right? It's going to almost go down to 0. Okay. If you plot the validation accuracy, it's going to look like this. Again, it's going to go up sharply, then plateau. And again, if you train long enough, it drops and never really recovers. Okay? And to be really precise, that bump here, the actual highest value, it could be sooner, right? You could have a bump here and then go down a bit and plateau and then drop. Okay. It's not necessarily top value and then drop. Again, I should fix that. So this is very, very bad, and it's called overfitting, which is a severe problem in machine learning in general. And overfitting really means you train so hard on your training set that you cannot predict anything else. Okay? The only thing you learn is to predict your training set. Your model is just too specialized now. It doesn't generalize to new samples. And obviously that sucks, okay? Because what you want to do is a model that generalizes well to new samples, to samples that your users will send to your apps, okay? So you need to train for long enough to get to that top accuracy, and this is obviously the one epoch you want to keep, okay? But it's difficult to forecast which epoch is going to be the best one. So what you really do is you train for long, right? You save the model at the end of each epoch, and then you plot all those accuracies, and you realize, oh, okay, I trained for 200 epochs, but actually the top one, the one with the highest validation accuracy is epoch 152, and that's the one I use. Okay. So you never know in advance which one is going to be the best. So if we sum things up, deep learning is about finding a local minimum, right? Not the minimum, because you'll never be sure you actually found the lowest point in that error function. Okay, it's been proven to be NP hard. If you don't know what that means, that's okay. You can ignore that. But it's very, very hard. Okay, it's the hardest problems in computing. Okay. So it's NPR, so you'll never know if you actually found the global minimum or not. All you care about is a minimum that's good enough for your business problem, right? If your business problem requires, let's say, 95% accuracy, and you get to 95.1, fine, good. Why would you spend more weeks and months trying to get to 97 if there's no business value in doing it? Okay? So you just need to get to some minimum that works for you. Okay? And of course, if you can find it fast, that's fine, because you can train faster, save money. And if you can find it again and again, that's fine too, because you will train many times, you will retrain with new data, and you will need to find that result again and again. Okay? And this is a really, really good definition of deep learning. All right, we're done with the theory, so let's look at an example now. Let's look at some code. So we're going to actually try something. We're going to work with a simple data set that I'm sure you've at least heard about. It's called MNIST. It's a data set of hundreds of digits, okay, 0 to 9. And you have 70,000 of those, 60K for training, 10K for validation. And we're going to try and learn those images. So we're going to try and do exactly what I described earlier. So we take the images, we flatten them into vectors, and we use a fully connected network to predict them. Okay? And I'm going to do this with a deep learning library called Apache MXNet, which is the preferred one for AWS. So I need to download the data set, which I've done before. I need to import MXNet. I'm going to train for 50 epochs. I've got an iterator to slice my data set into batches. Okay, so I don't need to worry about the slicing and dicing. That's done for me. And I'm going to build a simple, fully connected network. So that's my input layer. I call it data. Okay. And MXNet will size it automatically by looking at the size of these samples. I'm flattening the data, like I said. Okay, so the 2D images, which are 28 by 28 pixels, they become a vector of 784 bytes. And then I have a first fully connected layer with 1024 neurons activated by ReLU. Then I have a second layer, 512 neurons activated by ReLU. And then I've got the output layer with 10 neurons because I've got 10 categories because 0 to 9, right? And that's how I define my model, okay? Now I need to decide where to train, so I'm going to train on GPU because I'm not paying for my bills. I'm going to bind the model that I defined to the data set that I loaded in the iterator. And then I'm going to pick an optimizer. I could pick SGD, but I'm going to pick Ada Delta with a learning rate of 0.1. And then I'm training. Okay, we can actually do it live. Yeah. All right, and so what we see here is the batches, right, going by, and the epochs going by. Okay. And it's quite fast because it is a GPU and it is a very small data set. Okay, and so we'll get to the end of the 50 epochs, which I've done before in the interest of time. It doesn't take long. And then I can save that model. I get to 98.14 accuracy, or something, 98.14%. Okay, and I can save the model, so saving all the weights that I learned automatically. Okay, here's the accuracy I got. And of course now I could try it. So how good is 98.13, right? Sounds pretty high, but is it really good? So what I did is I drew some digits with paintbrush. Okay, recite them to 2828, and we're going to try and predict them and see how we do here. So all I need to do is to load the model that I just trained, okay, which takes about 4 lines of code, and then I can forward those new images into the model. So let's try this. Okay, so you can see my digits here, and you can see the outputs. Okay, so for each digit you see the 10 probabilities. Okay, remember that's what we read on the output there. We have 10 neurons, and we read the probabilities for each of the 10 classes. So the first value here is for class 0. So this is very high, which is great. You know, I've got 99.56% for class 0, and that's good. Okay. My 1 is classified pretty nicely too. The 2 is very nice, so don't let this fool you. There will never be zeros and ones. It's just because I'm stopping at 4 decimals and it's rounded up. Okay, so this really says it's at least 0.9999 something. Okay. So it works well for 3, works well for 4, 5, 6, 7, 8, and 9 is completely wrong as usual. Yes, some things in life are really predictable. 0, 1, 2, 3, 4. Okay, so the highest probability is for class 4. So my model here is confused by this ugly 9 and thinks it's a 4. Okay, so there you go, right? 98 point something accuracy, and then you try 10 and one of them is completely wrong. So the moral here is never really trust validation sets, right? Trust your own samples. Make sure you use ugly samples to validate models. So what did we do wrong? What did we do to those images? Remember? Yeah, we flattened them. So is that a good idea, right? Probably not, because, you know, let's say, you know, let's look at this 8, that cross here, right? If we could learn to recognize geometrical shapes, and we would learn to recognize this cross in the middle of the 8, and we would know for sure this is 8. This is an 8. Because no other digit has this, right? So when we flatten, we lose the spatial relationship between the pixels. So probably we lose the okay? So which is why when we work with images, we tend to work with a new type of network called convolutional neural networks. Okay, I'm sure you've heard about those. And convolutional neural networks are quite different because they work on 2D or 3D or multiple dimension data, right? They don't flatten stuff. And the basic idea here is that in a convolution network, you will have multiple stages. Okay, so here's 1, here's 2, okay? And these stages are usually the convolution operation followed by a pooling or subsampling operation. So let's explain convolution really quickly, okay? If you played with an image editing app, you've done this before, right? Convolution is about taking a small matrix like this, it's called a filter or a kernel, okay? And it needs to have the right values. And you just take it and start, you know, from the top left corner, and you slide it across the image, right? From top left to bottom right. And you run the convolution operation, which is just taking the pixel in the image, the pixel in the filter, multiplying them, and then doing this for the 9 pixels and adding all 9 into the new image. Okay? So that's what convolution is. Okay? Just sliding that filter and multiplying the underlying pixels by the filter pixels and adding everything into a pixel here. And you just do it again and again and again. Okay? And if you write the right values, you get to something like this. Okay? So you could call this one an edge detector, right? We have the edge of that weird beast. So if this was a dog or a cat or an elephant, we would have enough information left here to know it's still a dog or cat. And still, we threw away a lot of information, right? All the black pixels here don't have any information left. Okay, and that's what convolution does. It filters, it extracts features. Okay, so here the features are the edge. Depending on the values, you can do many different things. Okay, so that's what convolution does. And actually, you use multiple filters. And that's what the training process learns. You start with random filters, and using backpropagation and the exact same thing I explained before, you will learn the filter values that let you extract the features. Okay, you've probably heard that deep learning extracts features automatically. right? It figures out automatically what's important in pictures and what's not. This is how it does it, okay? It learns what value should be in those filters to actually extract useful information. And then, so you do this with maybe 20 or 30 or 50 filters because you want to learn to extract different features. You could learn to extract edges, you could learn to extract contrast, you could learn to extract vertical lines and all kinds of different things. So that's why you need multiple features. And then you run pooling, okay? And pooling is much simpler. Pooling is just about shrinking the image because as you can see here, we threw away a lot of information and we could throw away a lot of those black pixels as well. They don't matter, right? So pooling, and let's say we do 2x2 pooling, it's quite simple. You take blocks of 2x2 pixels and you just keep the highest one, okay? The highest pixel. Because the rationale is the highest pixel is the brightest pixel. Okay, so really what you want to do is keep the brightest pixels because if you stay here, right, if you have to throw away some stuff, you want to keep the bright pixels and you want to throw away the black ones that don't help in understanding what this image is. Okay? And that's how convolution works. So extract features, shrink the image, extract features, shrink the image again, or the images, and then you end up with a bunch of very tiny images that look nothing like the original picture, but they have the right information in them. And then you can flatten those and use a fully connected network. Okay. That's my best 3-minute version of convolution ever. Okay. Yeah. So there's much more to say about it, but that's the intuition you need to build. Okay. Intuition is very, very important in deep learning because the math and the theory gets crazy. And this is a very simple model. The state-of-the-art ones, they have hundreds of layers, but you need to understand what convolution really does. Okay. It learns the filters that help extract features. And once you've extracted features, you throw away the black pixels that mean nothing, and you do it again and again and again. And that's how you shrink very large images to very tiny ones while keeping the right information in them. Okay? So you can do all kinds of crazy stuff with this. I want to point out this open source library called BlueOn. It's actually an API on top of MXNet. It's quite new, BlueOn CB, which means computer vision. And the cool thing about this one is it has a collection of pre-trained models. Okay, so these are pretty advanced, or I should say very advanced, convolutional neural networks that can do classification, detection, segmentation, and it would be a lot of work to train those yourself, right? And it's not needed because some people have done it for you. So just go and take a look at BlueOn. You will see some examples. And it's really 5 lines of code to do each of those, right? Load the model, predict, print the results. Okay, and you can have state-of-the-art models to do crazy things like this. And of course, you could train them again on your own data. You could start from the pre-trained model and fine-tune them on your own data, right? To have the best of both worlds. And that works pretty well as well, right? So, interesting. Okay, let's do a quick test of today. So we're going to try MNIST again, okay? But this time we're going to try a simple CNN, and it's pretty much the one you saw on that slide, which is called LeNet, because it was invented by a researcher called Yann LeCun. So LeNet, right? French guy, top AI researcher working for Facebook. So that's pretty much what the network would look like, again with MXNet. So input data, a first convolution layer, a pooling layer, a second convolution layer, another pooling layer, and then flatten, and then use a fully connected layer to classify MNIST again into 10 categories. Okay, and you could literally read the research paper and code this stuff, right? Because you just work at layer level, and it's quite easy to do. We're going to train on GPU again. Okay, I'm going to use another optimizer. In the interest of time, I already trained. It takes a couple of minutes, no reason to waste them. And we get to 99.15. Okay, which is a bit higher than the fully connected one, right? But now we're careful, right? Because we got disappointed before. So how about we try again? So I'm just going to load that new model that I just trained, okay? And I'm going to predict my digits again. Okay, so zeros and ones and twos were good. They're still extremely good. If anything, they're higher than before. And 9, okay. Still not perfect, but this is the highest accuracy, this is the highest probability for the 10 classes. Okay? So this really says, okay, 0, 1, 2, 3, okay, it looks a bit like a 3, 4, 5, 6, 7. It looks a bit like a 7, but okay, if I have to make a call, I'll say it's a 9. So, see, you can still, you can still upgrade the model and try to actually get to classify that 9 more accurately. But generally, this is why we work with CNNs, because CNNs will learn the features. And it's quite possible that there's a filter in there that learns how to detect that cross in the 8. Right? It's quite possible it's in there. I should check. And this is really a distinct feature for the 8 digit. Right? So CNNs just work better. Question?
Could you do meta training here to tweak the parameters of the learning so that this result would release?
So there are many ways you could try to increase. You could have more layers, you could have deeper layers, you could have more filters. That's the fun part in deep learning. That's where it stops being scientific and it becomes cooking again, right? Cooking recipes. So you could do that, but I think what would really be interesting is inspect the filters, right? And specifically for low performing samples like this, predict them and inspect the layers and see which filters are reacting to what. And you could see why it thinks it's a 3, okay? Because it has that circle shape that could be a 3, right? And then, of course, the lower half doesn't look like a 3 at all. But it would be interesting to look at the filters, look at the layers, and see what gets activated by this and what doesn't. And maybe I just need more 9 samples, and maybe I just need more 3 samples to help the network say, no, this is really different stuff. Right? But yeah, there are many, many ways you can improve that. But it would mean looking in detail at the samples that don't really work, and then just try to understand why. So that's the fun part. Yeah? Really good question. So the question is, what these are black and white pictures, what about color? So if you have color pictures, basically the difference is, let me get to my slide. This one. Is that here we see convolution on flat things, okay, flat images, but you can do multidimensional convolution. So if you had a color image, you would have 3 channels, red, green, and blue. Okay, so each image would actually be it would actually be 3D. Okay, and you would run not a flat convolution filter, but you would run a cube. Your convolution filter would not be flat; it would be a cube, and you would run it on the 3 channels. Same idea, right? You would slide that cube inside that 3D shape, right? And now you need coffee, right? Oh yeah, it will take more time, and yeah, it will take more time. And convolution is why you need GPUs, because they are math-heavy operations. And if you run this same example on CPU, it's 20, 30 times longer to train. So convolution, and it's easy to parallelize convolution on the multiple cores of a GPU. Okay. So you're absolutely right. If you don't have to work with color images, right? If you can live with, if you get good results with black and white or grayscale, say grayscale, please use grayscale. It will save a lot of time. Okay. Okay. Just 5 minutes. So the last one I want to mention is it's yet another architecture, and these are called LSTM. So far we've seen fully connected and CNN, and these have no memory at all, right? You could take 100 pictures, predict them in any order, and you would always get the same results. Okay? It's really completely stateless, no memory. And that doesn't really work when you need to predict sequences. So for example, if you want to predict time series, if you want to do machine translation, when we translate, we don't translate word for word. Of course, we look at the word we're trying to translate, but we also look at the first words of the sentence. That gives us context. Okay, so this is why this LSTM neuron was invented, and in a nutshell, it has memory. It remembers the last few predictions, and so it does a really good job at text processing, machine translation, etc., etc. Okay, not going to go and explain this one. Again, feel free to dive in. It's not that bad. An example of a project using this is an AWS project. It's an open source project called StockEye that uses an LSTM architecture to build machine translation models. So you can grab that project, train with the, let's say, a Dutch to English data set, right? And build in a few hours, build a pretty good translation model. Again, it's all based on MXNet and an LSTM architecture. Okay, and to conclude, I want to show you the crazy stuff. And these are called GANs, which means generative adversarial networks. And, well, do you know who these people are? Any movie fans, TV fans? Yeah, you're all serious people. You don't watch TV, right? You have no time for that. No one? Sure? You're suspicious now. Well, you're right to be suspicious because these people don't exist. Okay? These faces have been generated by a GAN model. Okay? By looking at a data set called the celebrity data set. That's why they tend to be good looking. Because movie stars and some tend to be good looking. It's unfair, but that's how it is. I'll never be a movie star. The model learns how to build similar faces, and it's not cut and paste. You know, it's not the ears of one guy and the nose of another guy. You know, it's really people that look like the ones in the data set. Okay, and this is a TensorFlow project. What about this one? Remember when you were 5-year-old, you were drawing things like this, and mom and dad were so impressed. And if you have kids, you probably have this on your fridge, like me. Okay, it's called a semantic map. Okay, so different colors for different things. And researchers using a semantic map and the data set, of course, can generate images. So you give the semantic map, and the model automatically generates a realistic picture based on that semantic map. This is a crazy project. It's based on PyTorch. And you go and look it up. You can zoom in on those pictures, and there's a lot of detail. So fake news are going to be really, really interesting. Even more than they are. All right? All right. 30 seconds. This just came out. Did you hear about it? Deep Lens. You can order it from Amazon.com. It's available since June 14th. And it's a deep learning camera that is powerful enough to run image models on the cam. So you can train a model in the cloud or on your own machine, doesn't matter. And then you can deploy it to the camera, and you can run it locally on the camera. And it's pretty fun. And you can do things like this, right? So it's a picture of my TV. And this is an object detection model, okay? So it's live, right? It's a live video, but of course, I just took a picture here. And as you can see, the chair is correctly detected, and the sofa is correctly detected, the laptop, okay, as well. My son and myself are detected as persons, which is reassuring. And it's all running live on the cam with a model that you deploy there and a piece of code, a Lambda function that has been deployed to the cam and run locally. So it's fully autonomous. It doesn't need the cloud to predict. It just works on its own. Deep Lens. Pretty fun. You'll find lots of resources. So if you want to dive a little bit deeper, these are the AWS URLs for machine learning and the blog. The MXNet, BlueOn pages, right? If you're interested in BlueOn CV, you'll find it there as well. If you need to train at scale, I didn't talk about it today because I didn't have time, but you could be interested in a service called SageMaker that lets you train very, very large models on fully managed infrastructure, right? Ask me questions if you like. And of course, I'd be more than happy if you took a look at my blog, Medium, where I post lots of machine learning and deep learning stuff. I have a whole bunch of videos on YouTube as well from conferences and AWS summits and whatnot. So you might find stuff of interest there. And the notebooks, some of the notebooks that are used today are in that repo on GitLab. Okay, and feel free to grab those as well. All right, I'm done. Thank you very much. I'll stick around for questions, and thanks again for having me today. It was a pleasure. Thank you.